Okay, we're back, and we're about to do calculations with significant figures. The main point to significant figures is not just to know how accurately you know a number, but to know how accurately you know the results of the calculation. That's really the real utility of significant figures. So when you're doing calculations with significant figures, there's certain rules you have to follow that determine the number of significant figures your answer should have. Basically, that the accuracy with which you know the numbers that you're putting into a calculation, that's what determines the accuracy with which you can possibly know the answer. Think about it. If you have one number that you know really accurately and one number that you don't know very accurately, and you multiply them together, how accurately do you know the answer? Well, not very accurately, because of that one stinker that you didn't know very accurately. So we need to go over the rules for calculations. As is often the case, there are different rules for multiplication and division versus addition and subtraction. So we'll go over multiplication and division first, and then we'll go over addition and subtraction. Multiplication and division, when you do those, what you're concerned about is the total number of significant figures in each number that goes into the calculation. And it's actually the number that you know least accuracy that controls the accuracy with which you can possibly know the answer. So the answer should have the same number of significant figures as the input number with the fewest significant figures. So in other words, as I said a moment ago, the number that you know least accurately controls the accuracy with which you can possibly know the answer. And by input number, I mean the numbers that are going into the calculation. Okay, so we can look at an example here. If you take 1.003 meters and multiply it by 36.573 meters times 4.2 meters. The number that we get out as an answer would be 154.06749198. And units act just like numbers when you're multiplying or dividing. So if you have meters times meters times meters, that would be meters to the third power. Now, this is the number that your calculator will give you if you multiply these three numbers together. The problem is, like I said, calculators are not programmed to recognize significant figures. So the calculator will fill up the screen with numbers very often, and very many times, most of those numbers are fake in the sense that we don't really know those numbers with any certainty. So we're going to have to round this number off to the proper number of significant figures. And in order to do that, we need to evaluate the number of significant figures for each of the numbers that went into that calculation. So for 1.003, we've got a 1 and a 3, which obviously count as significant figures. But what about the zeros in between? Well, both of those zeros are between non-zero digits, that is, between numbers that are not zeros, so they both count. So that number has 4 significant figures in it. 36.573 does not have any zeros, so all of the digits count, and that's 5 significant figures. And 4.2 doesn't have any zeros either, so that's clearly 2 significant figures. That's the smallest number, and so that determines how many significant figures our answer can have. 2 significant figures. So what we're going to have to do is take that answer and round it off to 2 significant figures. We can keep the 1 and the 5 because that's the first and second significant figures, but everything else is going to have to go. Now, obviously, though, 154.086 whatever doesn't round off to 15. So there is actually a rule that any number that's dropped before the decimal point needs to be replaced by a 0 in order to maintain the magnitude of the number. So that 4 that gets dropped before the decimal point has to be replaced by a 0. Everything after the decimal point just goes away. Now, also when rounding off, you have to look at the first number that you're dropping and see what value it is. If the value of the first number that's being dropped is 4 or less, then the last number you're keeping can stay the same. But remember, if the first number you're dropping is 5 or greater, then the last number you're keeping would have to go up by 1. In this case, the first number being dropped is a 4, so there's no problem. The 5 remains a 5. So it's just 150 cubic meters. And I'll write down that rule I mentioned about the zeros. And that is, again, that any numbers dropped before the decimal point need to be replaced by zeros. And that's in order to maintain the magnitude of the number. So this number properly reported would be 150 cubic meters. And be careful not to put a decimal point after the 0, otherwise it becomes 3 significant figures. Okay, so that is an overview of multiplication and division. There is also a set of rules for addition and subtraction. Okay, so the rules for addition and subtraction are a little bit different. With addition and subtraction, you're actually concerned with the number of decimal spaces, not with the total number of significant figures. Okay? And so the answer should have the same number of decimal spaces as the input number with the fewest decimal spaces. So we're going with it's basically the same rule as it is for multiplication and division, only we're concerned with decimal spaces instead of total number of significant figures. Okay, so if we look at an example of this, 1.467 meters plus 7.436 meters plus 1.42 meters plus 3.6 meters. When you add units or subtract units, first of all of the units have to be the same, and the units for the answer will just be the same as the units that you're adding or subtracting. So there's no raising them to powers or anything. So our answer will be in units of meters. If you add all of these numbers together in your calculator, you're going to get 13.923. But that's actually too many decimal spaces, because if you look at the numbers here, The first number has 3 decimal spaces, 467. The second number has 3 decimal spaces, 436. The third number has 2 decimal spaces. And the last number only has 1 decimal space. That's the fewest number of decimal spaces, and so that's how many we have to have in our answer. So we have to round off this number so that it has only 1 decimal space. So we're allowed to have the first digit past the decimal point, but nothing else. So we have 13.9, and the rest of the number has to go away. Notice that the first number we're dropping is a 2, which means that the number before it can stay the same. So it's 13.9 meters. That would be the proper answer to the proper number of significant figures. Now, I mentioned about rounding off numbers, and so remember the rule is that if the first number you're dropping is 5 or greater, then the number before it has to go up by 1. If the first number you're dropping is less than 5, then the number before it can remain the same. If you're dropping any digits before the decimal point, they have to be replaced with zeros. And if you're doing a multi-step calculation, you only have to round off for the very last step. So in other words, you should only be rounding off for significant figures once during any calculation. And we'll get to some examples later where there are multiple steps in a calculation, and you just have to be sure that you're not rounding off more than once, because you can get into a situation where you're rounding off too much and the number actually starts drifting from what it really should be. Okay, so if there are any questions on that, you can always send me an email. I keep wanting to say any questions, but I'm probably not going to hear anything if I do, so I have to resist the temptation. Okay, next we want to talk about precision and accuracy in measurements. And we want to talk about these two categories because, of course, we always go for the greatest accuracy in measurement. We want our measurements to be as close as possible to the real value of what we're measuring. Well, a couple of problems. We can't always evaluate how accurate our methods are because in many cases we don't know what the true value we're measuring is. So it's hard to compare our measurements to the true value if you don't know what it is. So precision is actually used as kind of a stand-in for accuracy. We tend to measure precision in science instead of accuracy on the assumption that if you're careful about things, then good precision usually means good accuracy. Those two terms are related to each other, but they're not the same thing. And we'll get into that, the definitions and how they relate to each other in just a moment. We always go for the greatest accuracy in measurements, but it's still going to be true that every measurement involves some error. It's kind of a variation on nobody's perfect. And no matter how careful you are, and no matter how much you try to eliminate errors in measurements, you're never going to be able to do it completely. There's always going to be some error. There are, of course, various ways to minimize error. And we usually try to take advantage of as many of those ways as we can. But it's not always possible. Well, in fact, it's never really possible to eliminate errors completely. One way that we try to reduce error is by doing measurements multiple times and using the average of those results in our calculations. This helps because any random errors should cancel out. There are other types of errors that have to do with, say, things being out of calibration. And if your, if your balance is out of calibration, then doing the measurement multiple times is not going to help. But those are the kinds of errors that are usually relatively easy to avoid just by making sure that the instrument is properly calibrated, for instance. But it's random errors that you have to really watch out for, because those are the ones that are hard to eliminate. But like I said, one way that you can compensate for random errors is by doing multiple times. The standard is usually 3. You want to do most measurements 3 times and average them together and use the result. Because of time constraints in our lab, we usually only do measurements twice and average them. But ideally, you'd want to do it 3 times. And as I said, you might not know the true value. So how do you know how good your measurement is? Well, there are actually 2 ways to measure certainty. And one of those ways is accuracy. And that is sort of the, accuracy is sort of like the holy grail of scientific research. But like I said, it's often hard to evaluate, because in order to evaluate accuracy, you have to know what the true value is. Because accuracy is defined as how close your measurement is to the true value. And like I said, that's pretty hard to evaluate if you don't know what the true value is. So we've come up with another method that often can sort of give you a hint as to how good your accuracy is, and that's precision. And for precision, you have to do multiple trials at a given measurement, and then you can evaluate how close they are to each other. So precision is how close individual measurements in a series are to each other. And that, if you're doing multiple trials, you can always evaluate precision because you're evaluating your own results and you're evaluating how close they are to each other, and you don't have to know the true value in order to do that. And this is also known as reproducibility. That means that you're able to get the same result over and over again. Because if your results are really close to each other, then you're basically getting the same result each time. And so, as I said, that's easier to evaluate than accuracy is. because you don't need to know what the true value is. And it's a fact that good precision and good accuracy usually go together, but not always. And one example of that would be if your instrument is miscalibrated. So if you've got a balance, like a laboratory balance that you're weighing things on, ideally that balance would read 0 when there's nothing on it. But let's say you miscalibrate it. Let's say that it actually weighs 1 gram when there's nothing on it. Well, you could do a series of weighings of an object, and you could get exactly the same mass every time you put it on the balance. And that would be excellent precision, but every one of those numbers is off by a gram. And so you've got good precision, but poor accuracy. And so it's not always that they go together. You can actually look at accuracy and precision by using a dartboard analogy. And so you can look at accuracy versus precision with a series of dartboards, getting increasingly less circular as we go on. Now, of course, we're assuming here that in playing darts, you're going for the bullseye, because that's where the most points are. And let's say that you throw 4 darts, and one of them lands here, and one of them lands here, and another lands here, and another lands here. They're all pretty close to each other. So that's good precision. The average position of the 4 darts is right on the bullseye. And so that's also good accuracy. And that's generally what we want to go for. On the other hand, maybe you get the darts lining up like that. That's good precision. But it's poor accuracy because the average position of the darts is way off center from the bullseye. So that's good precision, poor accuracy. This would be an example where you might have a miscalibration going on. Okay, you might have, say, poor precision, but good accuracy. And this actually happens more often than you'd think. This could be caused by, say, carelessness combined with a bit of luck. Okay, and say one arrow or one dart lands there, and one dart lands there, and the third one lands there, and the fourth one lands there. So obviously the darts are nowhere near each other. They're all over the place. So that's poor precision. But if you take the average position of those 4 darts, it's right on the dart. It's right on the bullseye. So that's actually pretty good accuracy overall. And as I was saying, this happens more often than you would expect. You'd think that if somebody, is having numbers that come in all over the place, that their average would be off too. But actually, very often, the errors just seem to cancel out, and you end up with a pretty good average overall. Happens all the time in our labs. And it is also possible to have poor precision and poor accuracy. And this would likely be the result of carelessness without the good luck. And so poor precision and poor accuracy might say your first dart lands there, and your second dart lands there, and the third one lands there, and the fourth one lands, say, here. And so obviously you've got quite a spread in the darts. They're all over the place. But if you take the average position of the darts, it's going to be somewhere like probably up around here, which is way off from the bullseye. So precision and accuracy are both pretty bad in that case. So the types of errors that we often have to deal with are random error, and random error is just like it sounds, a result of random happenings. Maybe somebody jiggled the table while you were reading the maths on the balance. The balances in the lab are pretty sensitive, so if somebody jiggles the table, that's going to change the numbers, definitely. Maybe there was a gust of wind, or maybe when you were reading a ruler, maybe you got some dust in your eye and your vision suddenly went a little blurry, so you wrote the wrong number down. Random stuff like that. It's the kind of stuff that tends to average out with multiple trials. Generally, the more trials, the better. But the minimum number of repeats, or the minimum number of trials, is usually 3. More than that if you want to be really careful, but 3 is usually considered the minimum. And the other type of error would be systematic errors. Those are due to some specific factor. And a classic example of this, again, would be miscalibration. So the balance reads 1 gram when nothing is on it, so when it should read 0. These errors don't average out. So multiple trials really won't help you here unless at some point you notice that the instrument's miscalibrated and fix it. It's not going to help. And it's because of this that you can get this example, like with good precision and poor, whoops, there it is, good precision and poor accuracy. That tends to be because of stuff like miscalibration. Okay, the next section we want to go over is 1.8, but I see we're closing in on a half hour, so I think I'm going to call it here, and we'll pick it up again in the next